In section 4.3, we're going to look at concavity in the second derivative test. If you recall from section 4.2 that if f prime is positive, a function is increasing, and if f prime is negative, a function is decreasing. A function is said to be concave up if the graph is shaped like a valley. And if it's shaped like a valley or if it's concave up, the second derivative is positive. Okay, so you notice that f double prime greater than 0 means concave up. But also, if you look at the slopes of the tangent lines, a is very negative, less negative, less negative, 0, positive, more positive. We can also say f prime increasing is a justification for concave up as well. So these three things mean the same thing. Similarly, a graph is said to be concave down if the second derivative is negative, or, so f double prime less than 0 means concave down, or the slopes of the tangent lines are decreasing. So f prime decreasing means concave down. Inflection points are points where the concavity changes, and inflection points occur where the second derivative is 0 or the second derivative does not exist. So very similar to the first derivative with increase and decrease, but now we're just dealing with the second derivative. Okay, in this example, we want to determine where the following functions are concave up, concave down, and find all inflection points. So as soon as you see concavity, we are thinking second derivative. So 3x squared minus 6x plus 4 is the first derivative. And the second derivative would be 6x minus 6. So now we're going to figure out what makes the second derivative 0. And if I'm to solve for x, I would get x being 1. The second derivative is not undefined because it's a polynomial. So now I am going to do my second derivative number line test. Again, take 2 and 0. If I plug that into my second derivative, 2 makes it positive, 0 makes it negative. So therefore, my function is concave down from negative infinity to 1, and it's concave up from 1 to infinity. And I do have an inflection point where my concavity changes, and that's going to be when x is equal to 1. And to figure out the coordinate, I plug 1 into the original function, so I'm going to get 1 minus 3 plus 4 minus 5. That's going to end up being negative 3. So again, concavity is very similar to the increase-decrease, except now we're dealing with second derivative. In our next example, we have a quotient rule to start with. So I want to find the intervals of concavity again. So I have to take the derivative using the quotient rule. So it's going to be x squared plus 1 times 1 minus x times 2x. And this is all over x squared plus 1 all squared. So now I'm going to simplify this. And if I simplify this, I'm going to end up getting 1 minus x squared all over x squared plus 1 all squared. So there's my first derivative. Now to take the second derivative, I have to use the quotient rule again. Now when I take the derivative of the bottom, it's going to be the chain rule. So it's going to be 2x squared plus 1 to the first times 2x. And this is all over x squared plus 1 all to the fourth power. Now notice there's an x squared plus 1 common to all of these. So I'm going to factor 1 out or cancel 1 out. So this is just going to be x squared plus 1 to the first power times negative 2x. This one's going to be gone, so I'm going to be left with 2x times 2, which is going to be negative 4x times 1 minus x squared. And this is all over x squared plus 1 all to the power of 3. So basically, I've taken 1 x squared plus 1 out of all three terms. Now, if I simplify this, I'm going to get negative 2x cubed minus 2x. And if I distribute here, I get negative 4x plus 4x squared. Sorry, plus 4x cubed all over x squared plus 1 cubed. And if I simplify in the last step, I'm going to end up with 2x cubed minus 6x all over x squared plus 1 all cubed. So now, to figure out what makes the second derivative 0, because I have a fraction, I simply equate the numerator to 0. So I can factor out a 2x, and I get x squared minus 6, x squared minus 3 equals 0. And then I can factor this as a difference of squares over the reals. So I get 3 possible values where the second derivative is 0. It's 0, root 3, and negative root 3. So now I'm going to use my second derivative number line test. Negative root 3, 0, and root 3. Again, I'm going to use, say, negative 4, negative 1, 1, and 4. Okay, again, no matter what I plug into the denominator, because I'm squaring it and adding 1 and cubing it, the bottom is always going to be positive. So let's look here to determine what's going to make the numerator positive or negative. A negative 4 makes this negative, and this negative. It's going to be negative. Negative 1 makes this negative, this positive. 1 is positive, positive, negative, and 4 is all positive. So I know my function is going to be concave up from negative root 3 to 0 and from root 3 to infinity. And it's going to be concave down from negative infinity to negative root 3 union with 0 to root 3. And my second derivative changes at 3 places. The sign changes, so I have 3 inflection points. So my first inflection point is going to be f of root 3. And if I plug root 3 into the original function, it is going to equal root 3 all over root 3 squared plus 1, which is root 3 over 4. If I plug 0 into the original function, I'm going to get 0. And if I plug negative root 3 in, I'm going to get negative root 3 over negative root 3 squared plus 1, and this works out to be negative root 3 over 4. So again, the process is exactly the same. The only thing is this derivative was a little bit more challenging. Okay, here's a multiple choice question from one of the AP exams. It says the function f has the property that the function, the derivative, and the second derivative are all negative. Which of the following could be f? Okay, so let's think about what this means. If my function is less than 0, that means the graph is below the x-axis. If f prime is negative, it means the graph is always decreasing. And if the second derivative is negative, it's always concave down. So we can eliminate graph E right away because it is above the x-axis. So that one is eliminated. Okay, if the graph is always concave down, okay, well, let's look at first of all where the other 4 graphs are all below the x-axis, so they fill the first requirement, but they always have to be decreasing. So this isn't always decreasing, and this one is increasing. So I'm down to B and D, and if the second derivative is negative, it's always concave down, and notice that this one is concave down to about here, and then it switches to concave up, so my answer is only going to be B. Okay, this one here is a multiple choice question from the 2003 exam. Again, they're giving us the function 2x e to the x, and they want to know where the function is concave down. So I have to take the first derivative, which is going to be the product rule, so 2x times the derivative of e to the x, which is e to the x, plus e to the x times the derivative of the first, which is 2. And if I factor a 2e to the x out, I'm going to be left with x plus 1. So there's f prime. So the second derivative, again, the product rule, it's the first function times the derivative of the second, plus the second function times the derivative of the first. Again, if I factor a 2e to the x out of these 2 terms, I'll be left with x plus 2. Now again, we've seen questions like this before, 2e to the x. Whoops. Let's back this up a little bit. I want to figure out what makes the second derivative equal 0. Again, nothing will make 2e to the x 0 because it's an exponential and there's no transformations there. So the only time this thing is going to be 0 is when x plus 2 is 0. So when x equals -2. So a quick number line test with -2. If I use -3 and 0, no matter what I plug in here, this is going to be positive. A -3 is going to make that negative, and a 0 is going to make that positive. So I want to know where it's concave down, so that's where the second derivative is negative, and that's going to be the interval where it is less than 2. So my answer is A, or less than -2, sorry. Okay, number 17 is another multiple choice question. Again, it says, which of the following statements is true? And this is the graph of f, and they want us to compare the values of f of 1, f prime of 1, and f double prime of 1. Well, we know that f of 1 is 0, because we can read that off the graph. F prime means the slope of the tangent line at 1, and we know that the slope of the tangent line at 1 is positive. And if we look at the second derivative at 1, the graph is concave down at 1, so the second derivative is negative. So the lowest value is going to be f double prime, and then f of 1, and then f prime of 1. My answer is D. Okay, let's take a look at this question. This is a 2007 response question, and it wants us, first of all, we're told that f of x is the function k root x minus ln x, where k is a positive constant, and they want us to find the first and second derivative. Okay, well, before I take the derivative, I'm going to rewrite this as kx to the 1/2 minus ln x. So f prime is going to be k over 2 x to the negative 1/2 minus 1 over x, which is really k over 2 x to the negative 1/2 minus x to the minus 1. F double prime, the negative 1/2 comes out front. So this is going to be negative k over 4 x to the negative 3/2 plus x to the minus 2. That's the derivative of x to the minus 1. Now, question B is saying, for what values of the constant k does f have a critical point at x equals 1? And for this value of k, determine whether it's a relative max, min, or neither, and justify your answer. So if it has a critical value of 1, that means the derivative equals 0 when x is 1. So I'm going to take my derivative, which is k over 2, and I'm going to move that x to the 1/2 down and write it as a root x minus 1 over x. This equals 0 when x is equal to 1. And why is that again? Because it says it has a critical point when x is 1. So if I put a 1 in for x, I'm going to get k over 2 minus 1 is 0. And if I add the 1 over to the other side times by 2, k is going to be 2. So now if I plug 2 back into my first derivative, I'm going to end up getting f prime is going to be 2 over 2 root x minus 1 over x. So this is really going to be 1 over root x minus 1 over x. And now we're going to do a number line test at 1. And remember, in the original question, I have a domain restriction that x has to be bigger than 0. So I'm going to plug 1/2 and say 4. Actually, I'm going to use 1/4. So the square root of 1/4 is a half reciprocated. It's going to be 2 minus 1 over 1/4 is 2. It's going to be 4, and 2 minus 4 is negative. If I plug a 4 in here, the square root of 4 is a 2, which is a half minus a quarter. It's going to be positive. So therefore, x equals 1 is going to be a relative min, because f prime changes from negative to positive at x equals 1. So there's question B. Now question C is saying, for what value of k does the graph have an inflection point on the x-axis, and find this value of k. Now question K is fairly difficult, Okay, so but it's saying for what value of k would the graph have an inflection point on the x-axis? So if the inflection point is on the x-axis, that means that the inflection point has to be at the x-intercept. Okay, so first of all, to find the x-intercept, we take our original function and we let y equal 0. So from our original function, we're going to get 0 is equal to k root x minus ln x. So k root x minus ln x. So if I add the ln x over to this side and divide by root x, that's going to be k. And if I take my second derivative, and it says it has an inflection point, that means the second derivative has to be 0. So my second derivative was negative k over 4x to the 3 halves. So let's just write that down. Negative k over 4x to the 3 halves plus 1 over x squared. This is my second derivative. And again, if I isolate k in this equation, I'm going to add this over to the other side. I'm going to multiply both sides by 4x to the 3 halves. So these are going to cancel here. So on this side, I'm going to have 4x to the 3 halves divided by x squared is going to be x to the negative 1/2, which is really 4 over root x is equal to k. So now I have k equaling this and k equaling this. So that means those two things have to equal each other. So ln x over root x has to equal 4 over root x. And notice in this relationship, the denominators are equal. So therefore, the numerators have to equal. And if I convert this to exponential form, remember ln x is really log base e of the number x. So converting to exponential, it's going to be e to the 4th is equal to x. So I found the value of x, but the question, notice, is saying to find the value of k. So I can just plug back into here if I want. So k is going to equal 4 over the square root of e to the 4th, which is going to be 4 over e squared. So that question was a little bit tedious and a little bit challenging, but again, that's how you set that question up. And again, that might be a bit much for now, but I just wanted to show you the depth that some of the AP questions could go to. Okay, the last part of this first part of 4.3 is using the second derivative test for local max and mins. So here's what the second derivative test says for local max and mins. If I have a critical point and I plug it into the second derivative and it makes the second derivative negative, then that critical point has to be a local max. Remember, a critical point is where the derivative is 0, is undefined. And if the second derivative is negative, that means my graph is concave down. So the only possible critical point has to be up there, which is going to be a max. Similarly, if my second derivative is negative, my graph is concave up, which means that that point is going to be a local min. So we want to find local extrema using the second derivative. Well, same procedure as before. I have to take the first derivative first of all. So I get 4x cubed minus 16x. And I'm going to factor 4x out, and I'm going to get x squared minus 4. And then this will factor into x minus 2 and x plus 2. So my critical numbers are going to be when x is 0, when x is 2, or when x is negative 2. Now if I take the second derivative, it's going to be 12x squared minus 16. And now I'm going to plug all of my critical numbers into the second derivative. If I plug 0 into the second derivative, I'm going to get negative 16, which means my graph is concave down. So therefore, x equals 0 is a relative max. If I plug 2 into the second derivative, I'm going to get 2 squared is 4 times 12 is 48 minus 16. This is going to be positive. Therefore, x equal 2 is a relative min. and f double prime of -2. Again, -2 squared. Again, this is going to end up being positive. So therefore, x equals -2 is a relative net. So again, just another way to find local max and mins by using the second derivative. Okay, that concludes the first part of section 4.3. It was a bit long, but again, lots of information there. So there's an assignment. Give it a try. If you have any questions, check the answers on the website.